Hello everyone and welcome to lecture today. Today we'll be talking about the ratio and root test as well as power series. So the idea here behind the ratio test is that the ratio test is designed to answer the question, does a complicated series behave more or less similarly to a convergent geometric series? This is the question we want to ask. And it's the direct question that the ratio test will answer for us. Same thing with the root test. The root test also will answer this question. So recall that a geometric series takes the following form. Sum from, say, k equals 0 to infinity of a r to the k is going to be a plus ar plus ar squared, and so on and so forth. And this converges. The defining convergence property that we showed for the geometric series is that it converges only when r is less than 1. More specifically, when the absolute value of r is less than 1, or r is between -1 and +1, strictly. So the idea here is that for this series, the kth term of the series is given by ar to the k. So a0 is ar to the 0, which is a. a1 is ar to the 1, and so on and so forth. So what this is saying for us is that if we consider the ratio of subsequent terms in the series, we'll notice something special. a1 over a0 is ar over a, or r. a2 over a1 is equal to r as well, because it's ar squared over ar, which just simplifies to r. And more generally, for any term in this series, ak plus 1 over ak is going to be ar to the k plus 1 over ar to the k, which is equal to r. So what this means is that for the geometric series, the limit as k goes to infinity of the ratio of subsequent terms in the series is just equal to r. And more specifically, we'll say the absolute value of this, because is equal to the absolute value of r. This is going to be important when we write down the actual ratio test. So if this limit, the limit of the ratio of subsequent terms in the series is less than 1 for the geometric series, this is convergent. So the ratio test states the following. Says that now for a general series, so to let the sum of bk and k equals 1 to infinity be a general series, not necessarily a geometric series. And consider the following limit. The limit as k goes to infinity of the ratio of the k plus first term in the series to the kth term in the series. We'll call this rho for short. So if this is true, then the following is true. This is the statement of the ratio test. If this limit of ratios for a general series is strictly less than 1, then the series converges absolutely. Which means that the series converges, the sum of its absolute values converge, and we have very, very nice properties for absolutely convergent series. If this limit of ratios is greater than 1, then the series diverges. And if this limit of ratios is equal to 1, then the test is inconclusive. Which means we have to use another method to investigate the convergence of the series. So a good example series, we'll look at just one example to kind of see how to use this, would be the sum k equals 1 to infinity of, let's say, negative 1 to the k times k over 5. This is certainly not a geometric series, but we can still take this and do the ratio test on it. Our bk here, these are this function of k right here. In rho, this is the limit as k goes to infinity of the absolute value of bk plus 1 over bk. This is going to be the limit as k goes to infinity of negative 1 to the k plus 1 times k plus 1 over 5, and we'll actually make it a little more complicated. We'll make this 5 to the k. So it's 5 over 5 to the k plus 1. That's the k plus first term in the sequence, in the series. This is divided by then negative 1 to the k times k over 5 to the k. So we see that this is the same thing as the limit as k goes to infinity of k plus 1 over k times 5 to the k plus 1 over 5 to the k which from the product limit law is going to be the limit as k goes to infinity of k plus 1 over k times the limit as k goes to infinity of 5 to the k plus 1 over 5 to the k, which is just 5. This limit goes to 1, so rho is equal to 5, therefore this series diverges from the ratio test. We'll do one more example. We'll say the sum as k goes to infinity, or the sum from k equals 1 to infinity of the series k squared over 5 to the k, or the limit of ratios is going to be the limit as k goes to infinity of the absolute value of k plus 1 squared over 5 to the k plus 1 divided by k squared over 5 to the k. This is the same thing as the limit as k goes to infinity of k plus 1 over k squared times 5 to the k over 5 to the k plus 1, which is the same thing as the limit as k goes to infinity of k plus 1 over k squared times the limit as k goes to infinity of 5 to the k over 5 to the k plus 1, which is 1/5. And this limit you can show using L'Hopital's rule is equal to 1. So this is equal to 1/5, which is less than 1, which means that this series converges by the ratio test. So this is directly how we apply the ratio test. Let's do one more example, just to kind of show that we can do this in a wide variety of situations. This next example will be very important for showing certain results for Taylor series, which will be in the next lecture. Consider the sum from k equals 0 to infinity of 3 to the k over k factorial, where the factorial function is defined as being 0 factorial, it's 1. 1 factorial is also equal to 1. 2 factorial is equal to 1 times 2. 3 factorial is 1 times 2 times 3, and so on and so forth. So k factorial for k larger than 0 is just the multiplication of all integers leading up to that integer k. So for this example, this will be the limit as k goes to infinity of 3 to the k plus 1 divided by k plus 1 factorial over 3 to the k over k factorial, which is the same thing as the limit as k goes to infinity of k factorial over k plus 1 factorial times 3 to the k plus 1 over 3 to the k. Which is the same thing as the limit as k goes to infinity of this function, and k factorial over k plus 1 factorial is the same thing as 1 over k plus 1. Because if k factorial is equal to 1 times 2 times 3 all the way up to k, and k plus 1 factorial is 1 times 2 times 3 all the way up to k plus 1, and you divide these two things by one another, you're left with a k plus 1 in the denominator here. This is the same thing as the limit as k goes to infinity of 1 over k plus 1 times the limit as k goes to infinity of 3 to the k plus 1 over 3 to the k, which is 3. This limit is 0, so this is 0 times 3, or 0, which is strictly less than 1. Therefore, this series is a convergent series. Specifically, it's absolutely convergent. The root test is a very similar statement and is derived in a very similar way. Kind of the motivation behind the root test is the exact same motivation behind the ratio test. And the idea is, again, to consider the geometric series. For which we know that the geometric series, if you look at, this is the kth term, and you consider the kth root of the kth term, and specifically we'll say the absolute value of the kth term to be precise, because r could be positive or negative. The kth root of the absolute value of the kth term is going to be the kth root of the absolute value of a r to the k which is going to be the same thing as the kth root of the absolute value of a times the kth root of the absolute value of r to the k. Which is just the absolute value of a to the 1 over k times absolute value of r. And if we consider the limit as k goes to infinity of this kth root of the absolute value of the kth term of this series, this then is the same thing as the limit as k goes to infinity of the absolute value of a to the 1 over k times the absolute value of r, or the limit as k goes to infinity of a to the 1 over k, and that r comes out of the limit because it's a constant in the limit, times the absolute value of r. And for any real number a, you can say, we can show that the limit of this expression as k goes to infinity is going to be equal to 1. This limit is 1. You can show this using L'Hopital's rule. Therefore, this limit is just equal to the absolute value of r which we know for the geometric series has to be strictly less than 1 in order for the geometric series to be convergent. So the root test is saying almost the exact same thing as the ratio test, but for this limit right here, the limit of the kth root of the kth term of an unknown series. So we, for the root test, we'll say let the sum of bk from k equals, we'll say 1 to infinity, be a general series. We don't know if this converges, diverges, or what have you. The root test gives us the following statement. So we consider the limit, call it rho again. So rho is the limit as k goes to infinity of the absolute value of the kth term of this unknown series, and it's the kth root of that. So the absolute value of bk to the 1 over k. And just like the ratio test, we have 3 possible statements. The first is that if rho is strictly less than 1, then the series converges absolutely. If rho is strictly greater than 1, then the series diverges. And lastly, if rho is equal to 0, then the test is inconclusive. Which means we need some other means towards showing the convergence or divergence of this infinite series. And what's really nice about this method right here, and these convergence tests, is that they directly tell us whether or not a given series converges absolutely or diverges if they're not inconclusive. Unfortunately, if they are inconclusive, then we're going to have to apply a different means of testing to show convergence. But very often these are powerful enough to sort of help us out in determining convergence or divergence of a series. So what we want to go to next and show next is kind of use these in a more general scenario. And this is the topic of what are called power series. So far we've only used sequences of numbers to form series, but what if instead of forming a series from of infinite numbers, we form a series of infinite functions? In some sense, we have seen this. It's going to take a little bit of thinking to kind of rethink the geometric series, but the geometric series is a great example of what's called a power series. Or a series of powers of x. So a power series is any series of the following form. We have some coefficient that depends on k, and you multiply that by a power of x. So it'll be c0 plus c1 times x to the 1 plus c2 times x squared plus c3 times x cubed, and so on and so forth. A power series is, in some sense, like a polynomial, but with infinitely many terms in it. And we'll see that this idea of a power series actually is very, very, very powerful. It will lead us to a very powerful tool called the Taylor series expansion. The simplest example that I can give you of a power series that we've talked about already is the geometric series. A geometric series is a power series with a constant value for all of the coefficients. All of the coefficients are equal to just some constant value c. So it's c times cx, or plus c times cx, plus cx squared, and so on and so forth. And we know that this geometric series is going to converge only when the absolute value of x is less than 1. So the geometric series is a great example of a power series. And what we want to do is we want to kind of switch our viewpoint now to think of, these infinite series of functions. What we've shown is that this infinite series, the geometric series, converges to the function 1 over 1 minus x when the absolute value of x is strictly less than 1. So what you should you want to try to change your viewpoint to now is seeing that if you take an infinite power series, in general, this infinite power series, if it converges, could, and very often does, converge to a function of x. So an actual function of the variable that's being taken the power of in the power series. And specifically for the geometric series, it converges only on the interval when x is between -1 and +1. For any point x on that interval from -1 to +1, the infinite series, infinite geometric series, converges to the functions 1 over and 1 minus x. The reason why Taylor series are so useful, will be so useful, is because they will give us a method for calculating this power series for any suitable function, or for, I should say, a suitable enough function on a given interval. So let's see some more examples of other power series that converge and try to use what we know about our series to figure out what they converge to. So we'll take the following series. Consider the series from k equals 2 to infinity of 2 times -1 to the k times x to the k over 3 to the k. This is the same thing as the series from 2 to infinity of 2 times -x over 3, all raised to the k power, which is the same thing as a geometric series, starting at k equals 2, of 2 times r to the k, where r is equal to -x over 3. So we have to be careful here because we know that this is starting at k equals 2 here. So we have to kind of remember that, and remember that if we call S, we'll call S, say, the sum, the same sum starting at k equals 0, this is going to converge to 1 over 1 minus r when the absolute value of r is less than 1. So in terms of x, this is going to converge to 1 over 1 minus negative x over 3, or 1 over 1 plus x over 3. This also tells us where it converges to in x, right? This is the absolute value of r is less than 1, which is the absolute value of negative x over 3 is less than 1, which means the absolute value of x is less than 3. Or x is between negative 3 and positive 3. So this equality right here is only valid when r is less than 1 in absolute value, or when absolute value of x is less than 3. So lastly then, to figure out the full value, right, of the series starting at k equals 2, we have to take the series starting at k equals 0 and subtract out the first two terms. The first two terms are going to be 2, which corresponds to 2 times r to the 0, and then 2 times r to the 1, or 2 times r. So this series right here converges to s, which is 1 over 1 plus x over 3 minus 2 times x over 3, which will become positive 2 times negative x over 3, which will be positive 2 times x over 3. But it turns out then that this function is exactly the same as this infinite power series when x is between negative 3 and positive 3, or the absolute value of x is less than 3. So this is a very, very interesting and very kind of cool result. It gives us exactly the way of taking a given power series and having a hope of going through and actually getting the function that power series is representing on a given interval. And we'll see that we can actually use this ratio test and the root test to prove in general when a power series is going to converge. Let's just look at one more example to kind of show that we can kind of go through and do this in a wide variety of scenarios. One of the things that you can do is you can shift the center, it's called, of the power series. Say you take a power series of the form x minus 3 to the k, from k equals 0 to infinity. So this is called a power series that's shifted by 3, or the center point of the series, x naught, is equal to 3. In the other examples that we've shown, the power series are centered at 0. This one here is centered at 3. Nonetheless, we can still go through and figure out what what's called the interval of convergence is. Okay, this is the same thing as the sum from k equals 0 to infinity of r to the k, where the r here that we're using is x minus 3. And this will converge to 1 over 1 minus r whenever the absolute value of r is less than 3, or less than 1, sorry, because r here is coming from this series. Now in terms of x, that means that it converges when the absolute value of x minus 3 is less than 1, or when x minus 3 is between -1 and +1, which is when x is between 2 and 4. So for all x between 2 and 4, this equality is valid, and this then says that this is going to be 1 over 1 minus r, which is x minus 3, or 1 over 4 minus x. So what this tells us is that on the interval from 2 to 4, or for x from 2 to 4, this infinite series, for any x in that interval, converges to this function right here, the function 1 over 4 minus x. So in general, for a given power series, then we've seen that you can take and you can expand that power series about a general point. So in general, say if you have a power series that's expanded around a point, it's the same thing as having a sequence of coefficients times x minus the expansion point, x naught, to the k. This is the general form of the power series, where x naught is the center point. Of the power series expansion. So we typically call this value the radius of convergence around the center point. Because it gives you the total distance away from the center point of the power series that you can travel and expect the power series to converge absolutely. So for example, in this problem right here, the radius of convergence r is equal to 3. Because the distance away from, the maximum distance away from the center point, in this problem the center point is 0, the maximum distance away from that center point that you can travel is 3. In this problem, the radius of convergence is 1, because the maximum distance that you can travel away from the center, which is 3, is 1. In the previous example, in the geometric series example, for a standard geometric series, the radius of convergence is also 1. So what we're seeing is that we can go through and do this in general for a power series, hopefully, and maybe even figure out a formula. And this is exactly what we can do using either the ratio test or the root test. So suppose our series takes the following form. We have a general geometric series, a general power series of the form ck x minus x naught to the k. Where the kth term of our power series is directly given by this coefficient ck multiplied by x minus x naught to the k. if we apply the ratio test, or we look at rho, which is the limit of the absolute value of ak plus 1 over ak, this is the same thing as the limit as k goes to infinity of the absolute value of ck plus 1 times x minus x naught to the k plus 1 over ck times x minus x naught to the k. If we look at this limit simplifies to the limit as k goes to infinity of the absolute value of ck plus 1 over ck and x minus x naught to the k plus 1 over x minus x naught to the k is just going to be x minus x naught. So it'll be this times the absolute value of x minus x naught. And you remember from the ratio test that this means the following. It means that this expression right here has to be less than, strictly less than 1. The limit of these ratios has to be less than 1 to guarantee what's called absolute convergence. So if we rewrite this a little bit, that means that tells you that the absolute value of x minus x naught has to be strictly less than 1 over the limit as k goes to infinity of the absolute value of ck plus 1 over ck, which is the same thing as the limit as k goes to infinity of the absolute value of ck over ck plus 1. And if this limit exists and is equal to a number, a value, even if it is equal to positive infinity, we call this r, which is the radius of convergence. So this is a direct equation from our ratio test for the radius of convergence. And if you can apply the ratio test, which you can, to any series, this will give you the condition that the radius of convergence, or a condition for solving for the radius of convergence. Now, what's neat here is that we can do this for, in general, any series that we want to. And what's also neat is that we can do this same procedure to also with the root test as well. So a good exercise would be to go through the calculations that I just went through and get a similar expression for this radius of convergence, but using the root test. So the last thing that we want to talk about in this lecture is going to be what happens when we take the derivative or integral of either side of a given series expression, a given power series expression. And it turns out that we have a very, very strong theorem. And this states the following. It says that as long as a power series is absolutely convergent in a given interval, what this means is that we are within the radius of convergence R, or absolute value of x minus the center of the series is less than R, we can differentiate and integrate term by term. So for example, we'll do two examples. We'll do an example where we differentiate term by term, and we'll do an example where we integrate term by term. So if you consider the function 1 over 2 minus x, this is the same thing as the function 1 over 1 minus x minus 1, which is the same thing as the infinite series, the power series, from k equals 0 to infinity of x minus 1 to the k. Now this equality is only valid when the absolute value of x minus 1 is less than 1. This is directly using our power series, or specifically our geometric series rule for convergence. What this theorem is telling us is that the derivative of both sides can be computed. So the derivative, the x derivative of 1 over 2 minus x is the same thing as the x derivative of the sum from k equals 0 to infinity of x minus 1 to the k. Remember, this is only valid if our condition is satisfied. And I'll move this over a little bit more so we have some more space. But this theorem is saying that the derivative of the left-hand side will be equal to the derivative of the right-hand side as long as we're in the interval of convergence. So as long as we're within a distance of 1 from the center, which the center here is positive 1. So this is all valid only when x is between 0 and 2. But when this is equal to this, this theorem is telling us that we can take the derivative of both sides. Not only that, but that this derivative of this infinite sum will be the same thing as the sum of individual derivative of each individual term. So the derivative of the left-hand side is going to be from the chain rule. We can go through and show that it'll be negative times 1 over 2 minus x squared multiplied by negative 1, which is the derivative of 2 minus x. And this is going to be equal to the infinite sum from k equals 0 to infinity of k times x minus 1 to the k minus 1. And this is actually going to be starting at not 0 but at 2. Sorry, at 1. Because this summation right here is a summation 1 plus x minus 1 plus x minus 1 squared, and so on and so forth. So the first term goes away when you take the derivative here. So it really starts at k equals 1 now. So using this derivative theorem, or the differentiation theorem for absolutely convergent power series, we've just shown that the function 1 over 2 minus x squared is in fact equal to the summation from k equals 1 to infinity of k times x minus 1 to the k minus 1. Or it'll be 1 plus 2 times x minus 1 plus 3 times x minus 1 squared, and so on and so forth. So we've just proven this using this differentiation theorem. And this is only valid, right? This equality right here is only valid when x is between 0 and 2, because this theorem only works if you're inside the radius of convergence. So the main point here is that this is what's called term by term differentiation. And you have to be very, very careful before you do this, right? It's not always mathematically valid to do term by term differentiation or term by term integration on an infinite series. It only works if you're inside a region where the series is absolutely convergent, or where you're inside the radius of convergence. So let's take the same example and see what this tells us about term by term integration. So we'll take same series, 1 over 2 minus x, which we showed was equal to the infinite sum k equals 0 to infinity of x minus 1. This is only valid when x minus 1 is less than 1, or in other words, when x is between 0 and 2. So term by term integration says that we can take the definite integral of both sides of this expression, or the antiderivative of both sides of this expression, in that as long as this holds, so as long as we're within the radius of convergence, this definite integral is going to be the same thing as the term by term integral of every term in this series. And so the definite integral of 1 over 2 minus x is the antiderivative, or the indefinite integral of 1 over 2 minus x is the antiderivative of 1 over 2 minus x, which is negative times the natural log of the absolute value of 2 minus x plus c and this has to be equal to the sum from k equals 0 to infinity then of the antiderivative of each one of these terms in the series, which is going to be 1 over k plus 1 times x minus 1 to the k plus 1, and each one of these is going to have its own integration constant, ck, which is an arbitrary integration constant. But the idea here then is that we've just shown that negative times the natural log of the absolute value of 2 minus x is in fact going to be equal to, plus c, say, is going to be equal to the infinite sum from k equals 0 to infinity of x minus 1 to the k plus 1 over k plus 1 plus some arbitrary constant, which is again the sum from k equals 0 to infinity of ck. You can just call this an arbitrary constant d, and really, if you want to, the difference between these two sums, this value c and this sum right here, is also an arbitrary integration constant. So the nicest way of writing this would be to write it's the natural log of the absolute value of 2 minus x. This is equal to, say, this infinite sum plus some arbitrary integration constant d. We'll just relabel both of those. But this is what we've just shown by term integration. Now remember, this is only valid when x is between 0 and 2, because the geometric series radius of convergence is 1, and the center here is also x equals 1. So this term-by-term differentiation and term-by-term integration is only a valid procedure in the event that we are inside the radius of convergence. But you see very clearly, hopefully, that this process is giving us even more types of functions that we can get by doing term-by-term differentiation or term-by-term integration. Like that, we started out only being able to do geometric series, so that function 1 over 1 minus x is the beginning of the lecture, using what we know about geometric series. And we've subsequently gotten now to the point where we can get a wide variety of functions using this, using that 1 over 1 minus x is the summation of x to the k when the absolute value of x is less than 1. So we've used this to expand the possibility, or expand the number of functions, right, that we can get, or we can express using power series. And the last step here is to ask yourself, how exactly, given a function, can we take that function and construct a power series that converges to that function on a given interval? And this is called the concept of doing a Taylor series expansion of a function. This is the last topic that we'll talk about, and specifically in the next lecture we'll talk about this. It's kind of the culmination of all of this power series knowledge and the main theorem that we ended with in this lecture. But thank you very much for tuning into lecture today. I hope you had a great day and you learned something.